My research is about designing Provably secure cryptographic protocols. So what that means is we want to use cryptographic primitives to design more complex protocols. So the goal here is to replace the use of a trusted third party and instead only rely on our assumption of encryption, signatures, or commitment schemes. So this idea started like in the late 70s, early 80s with the famous problem of how do you play a card game over the phone? Like the issue when you play a card game over the phone is you don't necessarily trust anyone to shuffle or distribute the set of cards. And so what cryptographers want to do here is to design a protocol that is exactly explaining how to use the cryptographic scheme and also which messages should be exchanged between the parties to completely remove the use of a trusted third party. So starting from this quite simple application, the next obvious step, I would say, is to try to broaden it into like two more applications, right? And so the next step for a computer scientist is to ask whether or not you can compute any function instead of just playing card games. And it turns out you can. And that's the topic of secure multiparty computation. And so what secure multiparty computation, or MPC, is about is to have a set of parties that have inputs and they agree on a computation. And so they want to carry out this computation and get the output without ever having to disclose the input to the other parties. And that we know how to do. So my thesis was about studying and applying these MPC techniques. So we know MPC is doable in theory, right? But making it efficient in practice is another story. And so one of our first results during my PhD thesis was that we took the SPEEDS framework, which is a quite known multi-party computation framework, and we showed how to completely remove the need for a trusted third party. The thing is, initially, the SPEEDS protocol asks you to distribute some cryptographic keys, and for this task, it required a trusted third party. And so we showed a protocol to do this key distribution without having to rely on a trusted third party, basically completing the complete circle, so now you don't have to rely on anyone to compute the whole protocol. One of the applications of MPC is that of secure key management. So cryptography kind of moves the issue of securing exchanges of messages to that of managing cryptographic keys. And so traditionally in the industry, you manage keys using what we call hardware security models, which are specific pieces of hardware which are very hard to break into. And this piece of hardware holds your key and only exposes a very simplistic API which allows you to encrypt or sign messages. The issue is this piece of hardware then becomes like a single point of failure. And using MPC, what you can do is you can, instead of relying on a single piece of hardware, you can distribute random-looking fragments of the key to a big set of computers which are distributed all across the world. And the advantage of doing that is then a hacker would have to break into all these computers to steal the key instead of just having to break into a single computer. So another goal of MPC and privacy enhancing technologies in general is to enable collaboration between parties that do not want or legally cannot share the data. In theory, we could, for example, have hospitals gather and perform statistical studies on the union of the database. The advantage in doing so is that you end up with a much larger cohort of patients than you'd have if any single hospital would perform the analysis locally on their own data. I want to mention that this kind of solution has been deployed already in Boston for studying racial and gender gaps in wages without having private companies to publicly disclose the wages information. So after my PhD, I'll be working for a private company which is trying to bridge the gap between theory and practice in a couple areas of cryptography, namely homomorphic encryption, multi-party computation, and zero-knowledge proof. My job there will be a bit more applied than what I've been doing for the past 4 years at COSIC. But I really like the idea that we are at a point where the technology becomes available to a broader audience than just researchers.